Okay, everybody, we're live for the last lesson in the units, last lesson of the course. We're going to look at composite objects, which is not a particularly new idea, actually. All we're doing is taking objects that we already know how to calculate the surface area and the volume, and we're putting them together. So that's the definition of the topic. It's two or more regular 3D objects attached along plane faces. I guess the typical examples would be something like, well, suppose I took a cone and I set it on top of a cylinder. There's a good example. Or I could put a pyramid on top of a cube. Or I could put a pyramid on top of a rectangular prism. Those ones actually are fairly easy to do, as you're going to see. They get a little tougher when something like this happens. Suppose, for example, I put a pyramid on top of, say, a cube, but it doesn't completely cover the faces. In other words, the face of this base that it's sitting on doesn't completely cover this base here. When it comes to surface area, that's kind of the toughest kind we might ask you, is you have to think about the fact that the area of this shape here would look like this. It would have an actual hole in it. Something like that. What we won't do is we'll never actually have it so that this is hanging off the edge, or they're attached by an edge instead of a face. So we try to keep these fairly straightforward. But basically, these are the kinds of things that composite objects are. So the first one we'll do for an example is we'll do a pyramid on top of, boy, when I first looked at it, I thought it was a cube, but look at it carefully. Notice it's not a cube. How do I know it's not a cube? Yeah, that stupid 11 there, that's not a 10. So it's close to a cube, but it's not. So I got to call that a square-based prism and a square-based pyramid. Luckily for me, they exactly cover the same area when you put the two bases together. But let's think about this. This object here plus that object there equals that object here. Now, this object's surface area, you've seen me do this before. I like doing this. I like making myself a little schematic plan here. This surface area here is a square plus 4 identical triangles, right? This surface area here is 2 squares, right? The top and bottom are squares, plus 4 identical rectangles. But does that mean that there is 1 and 4 is 5, 6, 7? Does that mean that there's 11 faces on this thing? Actually, there isn't 11 faces on this thing. There's only 9. Count them. There's 4 on the top, 4 around the side, and 1 on the bottom. So how do you go from 11 faces to 9? Well, you lose 2 of the faces when you glue these two together. The way I like to think about it is, surfaces are only things that touch the air. Imagine if you glued these two pieces together and you glued them along this seam so that nothing could leak in, and then you dunk the thing into a can of paint. Surface area is all of the faces that would get painted. The stuff that's in the middle is not surface. So I lose this shaded and this shaded area. So kind of think about it, well, I lose this square and I lose one of those squares. So I think I'm ready to calculate my surface area. My surface area here is really going to be 1 square, which is this bottom, plus 4 rectangles, plus 4 triangles. So that's going to be the surface area of my entire shape here. Okay, looks good. So let's start calculating. Surface area is, let's do the square first. That's 10 times 10. I'll just write 10 squared. That makes my life easier. And then the 4 rectangles. All the rectangles are 11 by 10. 11 by 10, and there is 4 of them. And then I have 4 triangles. Now remember the formula for a triangle? It's base times height divided by 2. So that would be a base of 10, a height of 9, and divided by 2. And I like to make my life a little simpler. 2 goes into 4 twice. There we go. I can probably do most of this in my head. That's 100 plus 440 plus 180. And then when I add all that together, fairly simple one, I get 720 centimeters squared. Okay, oops, sorry, I'm off the screen. And I'm blurry. Oh, that's better. So there we go, 720 centimeters squared. So that's the surface area of that figure. And again, make sure you understand that it started off as two figures that had a total of 11 faces, but it ended up with only 9. Okay, got good news for you. Volume's actually much easier. It doesn't matter whether the faces overlap or not. They don't lose any of the space inside. So volume is literally just add the volume of these two shapes. Now, we do have a calculation we got to do before we do volume. What are we missing here? We don't know the height of this pyramid, so we better do that first. Okay, so let's see the height of the pyramid here. I'll just sketch it down here. Okay, so the pyramid is this guy here. I didn't draw that very good. Good enough. I need this height here, and if it's 10 all the way across there, that makes this a 5. We already know that the slant height from here to here is a 9. So I've got a triangle that is 5, 9, and I need that height. So height squared plus 5 squared equals 9 squared. So height squared is equal to 9 squared minus 5 squared. So height squared is equal to 81 minus 25. And 81 minus 25 is, let's see, what is 81 minus 25? Is that 56? I had to think about that. So the height's going to be the square root of 56. All right, so there, I've got all the numbers I need now. The volume of this entire object here is, I'll call it volume total, is equal to the volume of the pyramid plus the volume of the prism. So that's going to equal, let's see, the volume of the pyramid is 1/3 times the area of the base times how tall it is, which I just figured out is root 56. The volume of the prism is just length times width times height, or again, area of the base times how tall it is. And when I run all that through my calculator, you can try punching buttons yourself, or stop the video and pause it and then try the buttons, see if you get the same thing as me. I get 1,349.44 centimeters cubed. So there we go. So there's the volume of a prism with a pyramid on top. Okay, so that's example 1. Example 2, we'll stick a cone on top of a cylinder. So example 2 is a cone on top of a cylinder. So once again, it's basically this object plus this object equals that object. All right, surface area. Well, I've got everything I need. Remember that the surface area of this thing is pi r squared, which is the circle it's sitting on, plus pi rs, which is the curved part of the cone. This one, the surface area is 2 pi r squared, because there's a circle on top and a circle on the bottom, plus 2 pi r, which is the length around here, times the width, which is the height. Now, when I glue these two objects together, again, they've been nice to us. They've shaded the two colors. See those two shaded faces? Well, they're going to disappear, right? They're in the middle here. They're not part of the surface. So, when it comes to making a formula for this thing, well, I actually don't need that circle. And I don't need one of these circles. So I'll just get rid of the 2. See the logic in that? So my total surface area for this object here is going to be pi rs from the cone, 1 pi r squared from the cylinder, because there is still a circle on the bottom that it's sitting on, and the lateral part, 2 pi r h. And I think I got all those numbers, so I'm ready to punch buttons in. So again, this circle won't be surface, and same with that one. Okay, so let's plug in the numbers. R is 3, S is 5. R is 3, R is 3, H is 6. I think when you figure all that out, you get exactly 60 pi. But they wanted decimals, so that's 188.5. Oh, it's actually 0.495. But remember, when you round something like that, it does say to 2 decimal places. So show the 0. That is kind of important here. Your science teachers. Oops, sorry, I'm off the screen. Show that 0. Your science teachers will be very impressed if you understand that you have to show those zeros when there's significant digits involved. All right, so there is a cone on top of a cylinder for its surface area. Volume, again, volume's nice and easy, but I am still missing a number. Go back to this cone, and we need to find its height, because it gives us the radius of 3 and the slant height of 5. Okay, is everybody done with the top part? I can move up. There we go. Okay, so they give us the slant height of 5, they give us the radius of 3. I had somebody this morning who knew right away they didn't even need Pythagoras. What's the height got to be? 3 blank 5. No, it's not 2. Okay, well, we'll do it out then. H squared plus 3 squared equals 5 squared. H squared would equal 5 squared minus 3 squared, which is 25 minus 9, which is 16. Look familiar now? 4, yep, 3, 4, 5. That was probably the first triangle you saw when you first learned Pythagoras' theorem. Most Pythagorean triangles don't end up being whole numbers like that, but this one's called a perfect triplet, so it is. Okay, so my total volume is going to be the volume of the cone plus the volume of the cylinder. All right, what's the volume of a cone? Well, the volume of a cone is 1/3 of the area of its base, which is pi r squared, times how tall it is, plus volume of a cylinder is the area of its base times how tall it is. Now, I put a little note here. I think this is important to maybe write this down, because next to people punching buttons wrong, this is the most common mistake people make. In this formula, the R values are the same for both cone and cylinder. But, finish that sentence for me. What am I going to say? The R's are the same, but the heights are different. So, you know what some people do to make sure they don't goof that up? Yeah, put little subscripts on them. Call this one H sub cone, and this one H sub cylinder. There we go. Just do something in your formula so that you don't accidentally, oh, H is this number, and then use that same number there because you're not thinking. That's a really easy mistake to make. Okay, so now that we got that kind of cleared up, let's put in the numbers. 1/3 pi r squared, and what did I find? H was 4, plus pi r squared, and the h on the cone, what was the h on the cone again? Way back here, it was 6. I have to check that back, I forgot. Pi r squared 6. Okay, punch buttons. How's the fraction button going? Everybody able to use 1/3 in their fractions? Okay, if you do this properly, it actually ends up being 66 pi exactly, or 207.35 centimeters squared. Oh, sorry. Cubed, thank you. There we go. So that's cones and cylinders. One last one. What if we get hemispheres involved? All right. Let's do a hemisphere. All right. So example 3, we've got ourselves a hemisphere. Well, let's see if we remember something from the other day. Remember this from the other day? The formula for a sphere's surface area. That's how I draw a sphere. Surface area for a sphere is 4 pi r squared. So, if I cut that sphere into a hemisphere, I should have half of this. Oh, but wait a minute. I've created a circle. That's why the formula for this is surface area is, well, it's pi r squared for the circle I just created. New circle. And it's half of this for the dome part, which is 2 pi r squared. And then we realized yesterday that we could, or yesterday, Friday, that we could stick this together and call it 3 pi r squared. Okay, well now let's go backwards. In the example we're doing, the dome's the only part that counts. This part won't be surface because we're gluing it to the top of a cylinder. So instead of 3 pi r squared, I'm going to need 2 pi r squared. So that's the dome part. And then again, remember what a cylinder is? For a cylinder, well, there's a circle on the bottom, a circle on the top. So that's 2 pi r squared pi r h. But if I don't have that surface, because I'm going to stick a hemisphere on top of it, what changes about the formula? Somebody said we lose a 2. Which 2 do we lose?
2 pi r squared.
That one. So there we go. So let's put that together into our formula. So it's 2 pi r squared plus pi r squared plus 2 pi r h. And again, that's the dome. That's the circle on the bottom. And that's the lateral surface area, or sometimes we call that the label. And I think we have all the numbers we need. Except again, I could make my life simpler. 2 pi r squareds plus 1 pi r squareds. There's 3 pi r squareds. Yeah, let's make our lives easier. The less buttons we got to punch, the less likely we are to goof one of them up. Okay, so that's going to be 3 times pi times 18 squared plus 2 times pi times 18 times 32. And I think we're ready to punch buttons. This turns out to be 6,672.74 square centimeters. So there's the surface area of a cone cylinder combination. A cylindome. I made that up. There's no such word as cylinder. Okay, what about volume? Again, volume's easier. You don't have to worry about missing faces because you're not calculating faces. You're calculating space inside. So no space inside goes missing. So volume is going to equal the volume of my hemisphere plus the volume of my cylinder. Volume of a hemisphere is 2/3 pi r cubed, and the volume of a cylinder is the area of the base it sits on, pi r squared times how tall it is. Quick note, you're not going to be getting this formula on your formula sheet because we expect you can do this piece of reasoning right here. We expect that you could go, wait a minute, my formula sheet tells me that for a sphere, the volume is 4/3 pi r cubed. So if I take half of that, turn it into a dome, well, I'm taking half of this. So that's why the formula is 2/3 pi r cubed. Cool. So if that makes sense to you, this is something you should be able to come up with yourself. We're not going to give it to you on the test or the exam. All right, we're ready for numbers. 2/3 pi. Radius was 18. Pi, radius is 18, and my height was 32. No easy simplifications there, so I'll just let the calculator do the walking here. I end up with 14,256 pi's, which as a decimal is 44,786.54 centimeters. Oh, my pen's dying. Cubed. And that's it for composites, volume, and surface area.